Okay.
Okay, so I guess we'll just start now then. All right, thank you everybody for showing up to the first virtual Stars and Planets and Galaxies and Cosmology seminar. Oh no, I did that backwards. Galaxies and Cosmology and Stars and Planets seminar over Zoom. It's my pleasure to introduce the first speaker, Samson Johnson. He did his undergraduate at the University of Montana, and then he actually spent a year at the CfA working with me, helping to get Minerva online. And now he's in grad school and about to graduate at Ohio State, working with Scott Gowdy. You may have seen his recent press release on the free-floating planets, and now he's going to talk to us about Roman, which is what WFIRST is now called, and the survey to constrain Eta Earth. So welcome, Sam.
Awesome, thank you, Jason. So yeah, as Jason just mentioned, WFIRST was recently renamed. So if I still haven't gotten WFIRST out of my system, I still say it on accident sometimes, but know that if I say WFIRST, I really mean Roman. And so today, I think I'd like to also start off by saying thank you so much for having me. And I'm really excited to talk to you today about the Roman Galactic Exoplanet Survey, and specifically its prospects for constraining the frequency of Earth-like planets orbiting the habitable zone of sun-like stars. Now, the statistic is interesting in its own right, obviously, but to sort of set the stage, I'd like to talk about the future of NASA missions. Up next is obviously going to be James Webb Space Telescope, and that's going to be teaching us about exoplanetary atmospheres. And then after that is going to be the Nancy Grace Roman Space Telescope, which is going to teach us about cold planets, those far from their host stars. And that'll be, right now, is planned to launch 2025. But after that, the jury is still out. And that jury for NASA is the National Academy of Sciences Astro 2020 Decadal Survey. The Decadal Survey is right now considering at least 4 large mission concept designs or concept studies. And that's, those 4 are HabEx, LUVOIR, LYNX, and Origin Space Telescope. Of those, 2 of them, LUVOIR and HabEx, are being designed specifically with the capability to directly image and collect spectra of Earth analogs. And that's to be able to search for habitable conditions and biosignatures around nearby sun-like stars. But in planning these large missions to teach us about the habitability of other planets, one of the key statistics is the frequency of such planets. So that statistic is called Eta Earth, and is important in understanding the potential yield and survey design for large space-based direct imaging surveys. And right now, currently, our best estimate of Eta Earth is coming from Kepler. The Kepler Transit Survey discovered a few thousand planets, and from those is able to estimate Eta Earth. But Earth analogs sit right at the detection sensitivity limit for Kepler. And so generally, you have to rely on extrapolation from those planets with shorter periods or larger radii to be able to infer anything about this region of parameter space. So here I've got the plot from the Burke et al. Study in 2015, showing a number of different estimates for that frequency of Eta Earth, given different assumptions. And as you can see, this number varies by a factor of few, depending on what you assume about the survey. And they also include a few other studies previously to them. And it's even in the literature more recently in 2019 and 2020, and people are still trying to figure out exactly what Eta Earth is. So just to show why this is, here I've got a plot from Matthew Penny's work in 2019, plotting the exoplanet mass on the vertical axis and their semi-major axes on the horizontal. Here, the black points are those planets essentially discovered from the ground, and red is Kepler's contribution. And then a few solar system objects have their class photos included. And here we can see that Earth sits right at the edge of this cloud of points and is just outside of Kepler's sensitivity. So obviously inferring things about the frequency of planets in this region of parameter space, where you have almost no planets, is difficult. So what can we do about this? One avenue to be able to constrain that frequency is through Roman's Galactic Exoplanet Survey. So here is a simulated drawing of Roman detected planets here in blue, And as you can see, Roman is going to find a comparable number of planets in this basically empty region of parameter space, in this large cloud of points over a large range of planetary mass and semi-major axis. But notably, it's further out. And we can also see that Earth also sits on that edge of the sensitivity function for Roman. So it sits at the edge of this cloud of points. So what can we really say about the frequency from Roman? So that's what I'm going to be talking about today. But first, one of the things we need to worry about is how the habitable zone of host stars, of planets discovered on host stars by microlensing. So here in this cartoon I made, in green, I've got some prescription for the habitable zone following Kaparapu et al., their 2013 work. And this, as you obviously know, that the location of the inner and outer edge of the habitable zone is a function of the mass of the host star and also the host star's age. So here I just assumed a 4 gigayear-old population. Now for microlensing, the one key scale that we need to worry about is the Einstein ring radius. So what you need to know is that that microlensing is most sensitive to planets that have projected separations from their host stars that are near the Einstein ring radius. And so here, this value depends on the mass of the host star, but also the distances to the lens and the source. And it is proportional to the square root of the mass of the host star. So here, as your mass increases, your Einstein ring radius pushes further and further out. But it pushes out slower than the habitable zone does. So what ends up happening is that these two start to approach each other, and then the inclusion of distance. So here, if we assume that the host star is at 5 kiloparsecs, we see that the Einstein ring radius is just sitting basically slightly outside of the habitable zone. But when we have a host star, a lens star that's in close to the galactic bulge, this Einstein ring radius actually pushes closer and actually intersects with the habitable zone for high mass solar type stars. So this is this interesting interplay that'll come up later. So what would an Earth analog look like to Roman? What we need to do to understand that is understand the survey details for the Galactic Exoplanet Survey. So how Roman is going to look for planets, these microlensing events, is by monitoring about 2 square degrees just south of the galactic center, and it's going to do so over 6 72-day seasons. These 6 seasons are going to be spread out by around 4.5–5 years over the survey baseline, centered on the equinoxes when the galactic bulge is visible. And during each 72-day season, it's going to be performing photometry in its 1 to 2 micron wideband pass. That's the W146 band. And it's also going to have supplemental color observations done at a much longer cadence and some bluer band that's yet to be decided. Right now, we assume that it's this sort of Z-band, 0.8 to 1 micron band pass at about 12 hours. But that's going to be subject to change as the survey design evolves. Overall, Roman is going to produce about 10 to the 8 light curves, and from those detect more than 30,000 microlensing events. Of those 30,000 microlensing events, about 1,400 should show planetary perturbations, and so we should detect about 1,400 planets. So here on the right side, what we're doing to, as I said, investigate this frequency of Earth analogs is running new simulations of the microlensing survey, and here is a simulated light curve that Roman could produce. Here, the black points are the photometric points from the W146 band, and then red are from the Z band. And here we can see the broad magnification that comes from the host star, and then a small short timescale perturbation that comes from the presence of this about 1 Earth mass planet. The host star in this simulated event is almost exactly 1 solar mass, and the planet sits just outside of 1 AU. And so here we can see this, small percent deviation caused by the presence of the planet is going to be able to be characterized mainly because of Roman's high precision and high cadence. So remember that the duration of this perturbation is proportional to the mass of the planet. And so for an Earth mass planet, that's about a few hours. And we can see this deviation lasts about 6. So back to this picture. of what we could know about exoplanets after the Roman survey. So here I'd like to focus in on this region of parameter space, those sort of small mass, moderately separated or widely separated planets. So here from the new simulations that we're running is a simulated drawing of exoplanets. On the vertical axis here, I've got the planet mass. And then on the other side, I've translated that to planet radius using the mass radius relationship from Chen and Kipping et al. In 2016, or just Chen and Kipping, there's not an et al. So here planets are coded by their host star. So I've separated them into two bins. The large circles are those that have hosts that are more solar-like, greater than a half a solar mass. And then the small diamonds are those orbiting M dwarfs, lower mass stars. The blue region is planets that we'd expect to have a significant hydrogen or helium envelope. Those are your, sub-Neptunes. And then the green region are those that are more Earth-like, small terrestrial planets. Here, the gray box, I also forgot the horizontal, all I've done is scaled the semi-major axis by the bolometric luminosity of the host star. So the effect of this, right, is to push, planets orbiting lower mass stars further out. And so here, the gray region denotes the habitable zone for the sun. And as you can see, Roman will actually be able to find, a few planets in this region. But like I said before, the real power is going to be coming from extrapolation from larger semi-major axes and larger planet masses. So one thing that I definitely want to note is that we're going to be able to recover true masses more likely for Earth analog systems. So how Roman is going to be able to determine the true mass, well, remember first that microlensing is actually sensitive to the mass ratio between the planet and the host star. And so to be able to tell anything about the true mass of the system, we need to look at our main observable from a microlensing event, which is the Einstein timescale. Here, the Einstein timescale is really just the angular size of the Einstein ring radius, theta e, divided by the relative proper motion between the source star and the lens star. So during a microlensing event, the source and the lens star are almost perfectly aligned, but after some amount of time, because they have some proper motions, they'll separate. And so how Roman is going to be able to measure mu rel is by using its long baseline, that 4.5-year baseline, to look for the lens and source separation. So here, this was recently demonstrated using Hubble by Aparna Bhattacharya in 2018 to show that if you follow up a microlensing event, you can see an extended PSF, that when you try and fit that star with a single star PSF, it actually fails and there's some significant residuals. So by being able to measure both stars, the flux from both stars, you can fit that with two PSFs and be able to extract that relative proper motion. Because we're most sensitive to planets that orbit in the habitable zone of bright stars, solar type stars, we're going to be able to perform this mass measurement more likely, or this relative proper motion measurement more likely, because we'll be able to detect the flux and be able to fit for that relative proper motion between the two stars. And so there's also a number of other considerations that go into the Galactic Exoplanet Survey. One of the major ones is understanding Roman's sensitivity function. So why this matters, you've probably heard the phrase like know thy star, know thy planet. When it comes to Roman, what's really going to be is know thy galaxy, know thy planet population. So why that is because changes in the galaxy, such as, like, say, the bar angle, some slight shift in the angle of the bar will impact the lens distance distributions that are used to help infer parameters of the event, and also things like how is the metallicity distribution of potential host stars. And so in doing this, I've been co-advising an undergraduate, Abigail Aronica at OSU, on developing an in-house galactic population synthesis model. I'd also like to highlight that she is going to be applying to graduate school, so keep an eye out for her name in applications. And then other things that play into this is that the microlensing event rates and a subset of Roman's projected fields are currently not well constrained, but they're being mapped out by near-infrared microlensing surveys from the ground in the near-infrared, such as the main one is being done right now by UCURT. And then the final note is that the survey design is not yet finalized. And this really goes for all the core community surveys that Roman will conduct. So if it's for the Galactic Exoplanet survey or the cosmological surveys for the Type 1a supernovae or the weak lensing surveys, those are going to be open to general community input until basically launch. And then also the fact that even though Roman is in its advanced stages of development, the survey design is still changing based on updated mission design changes. For example, we recently received updated slew and settle times that could increase the number of fields that we monitor from 7 to 9. And finally, the work that I'm most excited about is the prospect of trying to combine Roman with Kepler. So these two monolithic surveys sit in complementary portions of parameter space here in the distance or the planet's orbital separation that they're able to survey. So here the real power is going to be able to be coming from the interpolation rather than extrapolation from one survey to constrain things like A to Earth. The hard part about this though is it's going to be a very complex sensitivity function. Kepler is obviously sensitive to planetary radii, Roman is sensitive to planetary masses, so combining these two is going to be non-trivial. So one of the main components of that is obviously the mass-radius relationship and how we relate planets' mass and their radius. And then the other parts of this, as I mentioned before, is how well we know the galaxy, essentially. So here, Roman is going to be obviously finding planets throughout the galaxy from where the Earth is to the galactic center. But there's a number of different stellar populations that it's going to be surveying in terms of like thin disk stars, bulge stars, and so on. And then the other thing, the obvious corollary of that is that are these the same planet populations? So would is a typical Kepler system going to be able to be relatable to a typical Roman system? And understanding this now is actually very important because it's going to inform precursor and follow-up observations and what we need to do in understanding, how well do we need to know these distributions. And with that, I'd like to end and, the takeaway point is that Roman is going to be sensitive to Earth analogs. It'll be able to find a few probably, and that the real power is going to be coming from Kepler and Roman combined. And I'd be happy to take any questions.
All right, great. Let's thank Samson again. And if anybody has questions, feel free to raise your hand and I'll call you in order, and then you should be able to just unmute yourself and ask. While we're waiting for the first questions, I'd like to ask, can you go back to the previous slide showing that plot of the sensitivity?
Yeah.
So when you showed the Earth analog that you found, it looked very significant, but here you don't have that many clustered around Earth. What sort of frequencies have you assumed in the simulation for Earth-like planets?
So for this particular plot, and I guess what we have been assuming is those found from ground-based microlensing surveys. So this is a mass function from Kassan et al. I think I have it written somewhere here. So basically, the mass function that we assume is the mass function that they measure is this here, this top part of the piecewise function, but we saturate it at at most 2 per star. With those that have less than 5 Earth masses. Sorry, I flipped the sign on that. So it's sort of, this is what we're assuming right now. Does that answer your question?
Yeah, so I guess why is there such a dearth of planets at 1 Earth radius? Are there other things that go into the detectability that make that example that you showed much less, typically much less significant?
Yeah, exactly. So in that sensitivity, right, is the projected separation is, I guess so the real thing is that example that I showed was extremely cherry picked. So I had to go through a number of curves to be able to find one that was worth showing. And so, yeah, so really getting down to the detection sensitivity, I guess the key parameters in there are, right, the mass of the planet, the short timescale duration, and projected separations and systems of the parameters of the system.
Great, thank you.
Yeah.
Any other questions for for Samson. I see Ryan raised his hand. Go ahead.
Hi, Samson. Great talk. Really interesting stuff.
Thank you.
I have a sort of remedial question just about microlensing in general. And so my understanding is, of course, you're measuring the mass ratio. That's fine, which means you need to know the mass of the lens to get the planet mass out, but you don't actually see the lens star. So my understanding is that you're just getting the stellar mass of the lens from the Einstein ring radius. So if that's true, how well do you typically how well can you measure the stellar mass from the Einstein ring radius? Or if that's wrong, just tell me what I'm missing.
I think your question is spot on, right? So what Ryan is asking, right, is the size of the Einstein ring radius is just proportional to the mass of the host star. What the issue is there's also the distances at play. So to actually get a constraint on the size of the Einstein ring radius, we'll probably, so that's work that I'm going to be doing mostly in the spring, is trying to figure out what Roman can tell us about true masses, whether we have to, you either have to assume something about the distance using that galactic model that I was talking about, or use another way to break this degeneracy. The most common is something like the microlens parallax. When you observe a microlens event from two different spatially separated locations, that'll give you a measurement of the Einstein ring radius, and you can start to break these degeneracies. So how well is right now an open question and is the subject of future work. Does that answer your question, or?
Yeah, it does. I'm just, now I want, two Romans to get.
Oh yeah. No, there's some thought of like, you might even be able to do it from the, so Roman is going to be at L2. And so is Euclid. So there, people, Matthew Penny and someone else, Etienne Bachelet, have looked at like, can you measure parallaxes from the intra L2 orbit of Roman and Euclid, or the other prospects are LSST or other ground-based surveys. That one that I might have not have mentioned, one called Prime from a group in Japan. So that concurrent observations is really going to be a key part potentially.
Okay, very cool. Good luck.
Yeah. Thank you.
All right, fantastic. I think we'll probably switch over to the other speaker and make sure we can get them set up. But let's thank Samson again.
Samson.
And yeah, bye.
Okay, so we're running a little bit early, which is great. So my name is Maren. I'm hosting the second speaker. As a reminder, this meeting is being recorded and we may post it online at a later date. So before I introduce our second speaker for today, we really want to encourage discussion. So feel free to actually interrupt during the talk, to ask a question if you'd like. And of course, we'll have a dedicated Q&A at the end. And so our speaker today is Pengfei, who just obtained his PhD this summer at Case Western University. Before that, he was doing a master's at Peking University in Beijing, China. He's currently a postdoc at Case Western. During his PhD, he studied dark matter with a sample of late-type galaxies, and now he's still interested in dark matter and modeling dynamic scaling relations in galactic clusters. Today, we're going to hear more about the halo mass function of these late-type galaxies from H1 kinematics. And Pengfei, just so you know, I may give you a 5-minute time warning. If it looks like we're running late, just don't be surprised if you hear from me after 20 minutes. But take it away. Thank you.
Okay, thanks for the introduction. So I'm very glad to present part of my thesis work at the CfA seminar. So my talk is mainly based on the paper, the publication in Aperture Letters. Within 20 minutes, I will have to skip a lot of details. So if you're interested, you can read this paper and also refer to the other paper which are closely related to this work. So today I'm going to present an empirical way to measure the halo mass function. So first, let's review what's the mass function. So within in the current galaxy formation model, galaxies are formed within dark matter halos, which are seeded from initial fluctuations. So the CDM model makes prediction about how many dark matter halos are formed. So this is quantified by the halo mass function, which is defined in this equation. So the capital M is the halo mass function, the little n is the halo number density. So the halo mass function psi m describes the number of dark matter halos per unit mass per unit moving volume. So though predicted in the model, but this quantity is very difficult to measure, because to measure this quantity, you have to have a large sample of galaxies with well-determined halo mass. But dark matter halos are invisible, so halo mass is very difficult to determine. So instead, what's measurable is stellar mass function. So I took this picture from Bollock 2017 annual review paper. So they present the stellar mass function measured in gamma, what they really predict in the model is the halo mass function shown as the black solid line. So these are two different quantities. So we are comparing apple to orange. So to do a comparison between apple to apple, the simplest way is to assume a linear correlation between halo mass and stellar mass using the cosmic value of baryonic fraction. So what Bollock did is to get the stellar mass function just come by multiplying the baryonic fraction by the halo mass. So what they get is, but this simple way results in huge discrepancies at both high halo mass and low halo mass. This means the map between stellar mass and halo mass must be nonlinear. So as this figure shows, at low halo mass with in power index beta, and at high halo mass, the power index would be minus gamma. This is the so-called abundance matching relation. So it implies dark matter halos of different mass convert baryons into stars with different efficiencies. So this relation is derived by comparing data to model. So we want to what data sets. So we can imagine if there is a function which map from some easy observables to the halo mass. So then we can derive the halo mass for a lot of galaxies. So for the easy variables, we can choose the hydrogen long waves, which is easy to measure because we only measure one value for one galaxies. It does not have to be specially resolved. So once we have the hydrogen long waves and halo mass, we want to know the functional form between these two quantities. So to work out this functional form, we use the rotation curves of the spark galaxies. So the spark sample includes 175 light-hour galaxies, spanning about 5 decks in luminosity and 4 decks in surface brightness. So it includes dwarf irregulars and large spirals. So very wide range in luminosity, surface brightness, and morphologies, as well as gas fraction from almost 0 to 0.9. So what makes it ideal for those tests is it has near-infrared photometry. So the mass-to-light ratio, because we want to derive the stellar mass, the mass modelings. So we have to use the stellar mass-to-light ratio, which varies very little at near-infrared, and it also has the high accurate rotation curves measured traced by the H1 and to large radii and H alpha deep into the center of galaxies. So we determine the dark matter halo mass for those galaxies by fitting their rotation curves. I show one example galaxy, IC2574, using the dark matter halo model DC14. This is the fit we got. Different lines represent different contributions from each component, like stellar disk, blue line, and the gas, the green line, and the dark matter halo contributions is black dotted line. The total rotation curves is shown as the red solid line. We see a good comparison. So this figure is obtained using the DC14 model. We also tried other halo models like pseudo-isothermal profile, Burkett profile, NFW, and ISO DC14 core NFW profile. And we also defined an empirical halo profile in this paper, which we call Lucky 13. So for 5 those halo profiles, we impose both flat price and lambda CDM price. for details about those models and the lambda CDM price, you can see, please refer to our APJS papers. Remember, this is only one galaxy. We have 175. So I also show a lot of examples here. So this is another 25 rotation curves. So we got a lot of dark matter halos. So for those galaxies, we determined their properties of dark matter halos, like the scale radius and characteristic volume density and halo mass. So the three halo models marked by red color are going to be used in this talk, NFW and DC14. They are all motivated from simulations. So we derived their halo mass around 11, and we can see they have very small uncertainties. And for different halo profiles, they could have different halo mass, but they agree at roughly 3 sigma. So you're all welcome to using these results. So we have, so for 175 galaxies and 7 models plus 5 additional lambda CDM price, we got totally 2,100 rotation curve feeds. So we will determine their halo mass. And also for hydrogen line widths, the spark galaxies have well-measured hydrogen line widths. There are 2 common definitions about the hydrogen line width. One is WP20, WM50. And WM50 is defined as the 50% of the mean flux density. The mean flux density is calculated within the defined box, the flux density. And also the WP20 is defined as the width at 20% of the peak flux. It's not the mean flux density, it's the peak flux density. So we have all those measurements, then we can map the functional form between hydrogen line width and dark matter halo mass. So, but though we'll determine the functional form, but we cannot use the spark galaxies to measure the halo mass function because they are just nearby galaxies and they are not complete. So what we use is the high pass galaxies. So the one you selected about 1,400 galaxies, and they measured the velocity function. They defined the half line width as the circular velocity. Though these velocities were measured in their paper, but this is not directly comparable to the CDM prediction. So we want to measure this function. This is the correlation I showed before between the hydrogen line width and the halo mass, dark matter halo mass, using the anisotrope profile. And we're using the Gaussian process regression to describe this relation. So we don't assume any field function, just using the data as a relation and told about the data. And this is the black solid line is the mean relation we got using GPR feeds. And also we did that for using other 2 halo profiles, NFW DC14 profiles, because their halo masses are a little bit different. So with these relations, we can derive the halo mass for galaxies in the high pass survey. So just based on their H1 line width measurements. Before heading to measure the halo mass function, we want to test our empirical method. So the cell mass function, cell mass of the spark galaxies also well measured. So we work out the relation between the cell mass and the hydrogen line width and got this figure. And the solid line is the mean relation we get. Use this, we derived the cell mass for the high pass galaxies and measured their cell mass function. Cell mass function, as we said before, is measurable. So there are some other measurements in gamma by Moffat. The dashed line shows the cell mass function for all galaxies, including early type and late type galaxies. But since high pass galaxies are H1 selected, so they are more comparable to disk-dominated galaxies. So the solid line is the result we want to compare. And we got a perfect agreement. So we think our method works very well. So now we are heading for the measurement of halo mass function. And this is the result we got using the anisotrope profile. the red line is the prediction of dark matter simulations. And we see a very good agreement at intermediate helium mass, ranging from 10.3 to about 11.7. We see a big discrepancy at large helium mass. So this is using the analysis. We also did this for another two halo profile, the NFW and DC14 profile. We see we got a very similar results. The shape are very similar, and those results are well fit by Schacht function in this relation, as shown by the black solid lines. So one interesting point we would like to make is the cosmic matter density fraction, because the helium mass function defines how abundant the number density of dark matter halos per unit helium mass. So if we multiply it by the helium mass and integrate within some range, we got the mass density, the dark matter density. So if we divide it by the critical density, we got the mass density fraction. So when we do this, integrate this within the range we have measurements, which is about 10.3 to 12.7 or 12.5. So we got the density, dark matter density fraction about 0.03. Even if we integrate this function from 0 to infinity, we got a density fraction about 0.04, which is about only a tenth of the cosmic value dark matter, cosmic value of the matter density fraction. That means most of the dark matter are not associated with galaxies. So we see the big discrepancy at large halo. So one possibility would be that high-pass galaxies are H1 selected. So probably the sample meets a lot of gas-poor galaxies. So we want to do a quick check. So one way is to look at the IllustrisTNG simulations. The TNG simulations include incorporate baryonic physics. So we can find their halos. We analyze the simulations and define their halos, and also calculate the gas fraction. This gas fraction is defined in this equation, which is m gas over the total baryonic mass. So we will set a very simple selection effect for these simulations. If we set the gas fraction larger than 0.1, then we get the helium mass function from the TNG simulations as presented by the blue solid line. So which does decrease a little bit at a large helium mass, but still way higher than what we measured. So if we continue increasing the criterion from 0.1 to 0.4, we got much lower. We do get much lower helium mass function, and potentially agree with what we measured at the large helium mass, but at the intermediate helium mass, the discrepancy appears and becomes larger and larger. So this could, but we note another factor is what really the observation, the selection criteria in observations is the flux density, not the simple total gas fraction. So probably this selection could be could be modeled with more with future work, like we choose point and do simulate the process of how the galaxies are selected based on their flux density. But currently we got a big mismatch at large helium mass. So to summarize, so we provide rotation curves for 175 galaxies using 7 helium models. So we determine their dark matter helium mass and show the strong correlations between helium mass and H1 line width. So, but we detect no problem analogous to the missing satellite problem. It's not the missing satellite problem because the minimum helium mass we probed is is about 10. So which is still much more massive than satellites. So, but we do find the perfect agreement at intermediate helium mass. But the huge discrepancy at high helium mass remains an open question. Could be due to a selection factor, or the simulated galaxies are too gas rich. So I'm ready to take questions. Thank you.
Thank you very much, Pengfei, for the clear and interesting talk. Yeah, if I could ask the participants to raise their hands to take for questions, that would be great. I guess in the meantime, I will ask a question. Sort of fairly early on in the talk, you had the slide that showed all the different models that you explored for your sample of galaxies. Yes. So I was just wondering, sorry, actually the list of different models. I'm familiar with the NFW and the INESTO, but could you just tell me a little bit more about what the DC14 model is and why you chose that one, why you chose those 3 out of that list of 7 possibilities?
Okay, yes, that's a good question. So all those head models, as well-known, NFW is a well-known profile from dark matter only simulations. So, but later on, they improved their simulations, and they found their simulated halos are better described by the INESTO profile. So, but for INESTO profile, they still use the dark matter only simulations. So for DC14, they introduced baryonic feedbacks, which is the supernova explosion. So what the aim is to solve the Casper core problem. So they want to use the supernova to eject a lot of dark matter halo mass, dark matter particles out, so to decrease the central density of dark matter halos. So the DC14 profile is also motivated from the simulations. But we do show in these papers, DC14 provide a much better description in rotation curves than NFW profile. So we believe the INESTO profile and DC14 profile are more prospective than the NFW profile. So we would like to use this. We use NFW just because it's very well known. We think probably people want to know what the result we would get using this profile. And the other profile we don't use because mostly they are introduced empirically, like C2 as symbol, the Burkett profile. They are good at fitting rotation curves, but we don't understand them. So.
Okay. Thank you for that. Were you able to, so did you look at the other fits at all to determine if there was anything interesting hidden in all that plethora of fits, or not particularly?
Can you repeat the question again? Sorry.
Oh, I mean, you gave a pretty compelling explanation for why you chose the 3 models that you did choose, but I was just wondering if you looked at all the other models, all the other fits that you did, if you used that for anything, or if you found anything interesting hiding in all those fits, or if you haven't pursued that.
No, not yet. One of the reasons is those profiles, like the empirical one, though they can fit those rotation curves, but what they probably they would return a very different halo models. But we could, so like in this model shows, so like for the pseudo-azimuthal halo profile, you get a much higher halo mass. So like for this core NFW profile, get a 14. So this is a very massive galaxy. This would be a very massive galaxies. I think those values are more trustworthy than those. Mm-hmm. And also you see their uncertainty is much larger, these profiles. So we tried 2 most trustworthy ones, and did also NFW found they're similar.
Okay, thank you. Are there any questions? I see one from Vadim. Go ahead.
Hi, yeah, thanks for for a great talk. So I had a quick clarification question. In the slide where you showed comparison with illustris, so what is F gas actually? Is it the fraction of gas in the halo or in the galaxy?
You mean the gas fraction cut?
Yeah. So what exactly M gas and M star here? Is it like the total stellar and gas mass in the halo, or
those are cut for the simulated galaxies. So in this simulated a lot of galaxies, and with the gas mass and the halo mass and stellar mass. So we don't select all those halos. So if we select all those halos, we would get the red line. This is the prediction of their simulation, the same as dark matter only simulations. But if we select only part of them, but according to the criterion of the gas fraction, then we get a smaller halo mass function because we ignore some. They have the gas fraction lower than our criterion.
Okay, so it's the gas mass and stellar mass of the central galaxy in the halo of a given mass, right?
Yes.
Okay, and one more quick question. So you did you try applying this method for the simulated galaxies, basically fitting the rotation curve, deriving this relation between?
I'm sorry.
Could you try? Did you try like repeating your method on the simulated galaxies like this to check whether you can get back this?
The point. I tried for what?
Basically applying the same method but on the simulated galaxy, so you can fit the rotation curve, derive the halo mass from that, and then find the correlation between line width or like
okay. They don't have the okay, that's a good question. So you want to check the relation, what we get there, right?
Right, yeah. So just to check if the method
like this relation. We didn't check that. One of the reasons is we don't have the line width measurement. So the hydrogen gas, this would be yeah, that's a good suggestion, in fact. So it's a consistent check. Yes, it's a very good suggestion.
Yeah, and I would also check that if you repeat the same procedure with the, let's say, with the illustris, so that you get the same mass function as the one you get just directly from the halo masses model in the simulation.
Yeah, it would be good consistency check. Thanks for suggesting.
Thanks.
Okay, any other questions?
I had a quick one. Sorry, I can't raise my hand because I'm a co-host. So I missed this, I think, in the beginning. This is for all types of galaxies or just spirals, or what was the high pass sample?
The high pass sample are H1 selected. So this is what we call H1 kinematics, because we don't H1 kinematics.
Yeah.
Because for gas poor like elliptical galaxies,
yeah,
they generally missed from the high pass self-survey.
Okay, gotcha. Yeah. And I was trying to think of like, so for that discrepancy at large halo masses, did you look for any correlation like halo properties for that might? Are there any? I'm trying to get like correlations in halo properties that might cause this too. I don't know. I don't know if that makes sense. It's outside. This is obviously outside of my field.
Well, it's good suggestion, but I guess the reason is probably we want this if we want to match the observation and the prediction, so we have to increase this much bit. But what we get does not show that this is not what we get from the data. So this function, the relation does not match that. So though we have a large scatter, but the scatter is, as we see, the discrepancy is larger than the error bar allows. So
awesome.
That's
Thank you. Yeah.
Okay. Any last questions? All right. Well, if not, thank you, Samson and Pengfei, for the great talks and for being so on time. We're actually wrapping up early. a reminder that both speakers are available for one-on-one meetings today, virtual meetings, obviously. And look in your email inbox for that information if you'd like to sign up. Their schedule is available online. But yeah, thank you so much, and have a great day, everybody.
And thanks for hosting us.
Thank you.
You're very welcome.